Hello. 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 I am sort of here. Hold up. Bear with me for a minute. I don't even know if you've already beaten me to the there's Alani. All right. So she wins. Hello, and there's Amanda. All right. And they are wait, silence. Oh, and there's Cheska, and they are sort of in the same hello, hello, hello. And Yavi. Wait, okay. So it's a silent study. Me too. And Chris. Okay, I see what's happening. I see how it is. I see how and hi you. Wait, but hi you is also a okay. Anyway, I'm gonna stop. I woke up sick. What? And she smiled and oh, right. Weird. That is so weird. That's awesome. That's very cool. And then okay, I should stop. Oh my God, the whole Yavi thing. Okay, Cheska, yeah, okay, that is it. And is Hayu part of this also? Or is Hayu wait, and yeah, she no, that's a oh my God. Okay, that's like the weirdest. Okay, all right. Way to I mean, I guess it's only fair. I guess I mess with your minds on a twice a week basis. You might as well mess with my minds all the time too. But then it's weirder too because you could oh, wait a second. I know what part of the weirdness is. It's not only all the camera angles and everything, and but it's also that they can hear each other. Right. They have there's like an audio advantage because you get it. All right. Anyway, whatever. All right. Hold on. I'm looking at the chat and we're going to start. Oh, the chat is them. Okay. I'm going to say hello to Melita and Freddie first because enough with those people. And Marilyn. Hello, Marilyn. Hello, Melita. Hello, Freddie. I'm just kidding. It's not enough.
Hello.
Hello. Oh, and she even said hello. So now, all right. Thank you. Okay. And we only need one person to listen. Right. This is so interesting. All right, there's going to be a new portal based on this whole madness. But it does. Okay, and sorry, I didn't say hello to Freddie or good afternoon to Freddie and Matthew. Good afternoon, and Marilyn. Good afternoon, and who else? And did I say Michelle and wait, and Michelle just turned. Oh, there's Michelle. Now is Michelle. Okay, I'm going to stop asking questions. But you're on the 8th floor. I mean, she's on the 8th floor. No, is that no, that's like that weird thing between 1 and L or whatever or
No, I'm on the 3rd floor.
the 3rd floor. Oh, the 3rd floor. Okay. Yes, I've heard of that. If memory serves, the 3rd floor is somewhere in between the 2nd and the 4th, isn't it? Okay, no, that's yeah, all right, the 3rd floor. Right. We just meet. Okay. I will wait, you volunteer. Wait, what? That's funny. Okay. You ever notice one? You know what? Okay, no, we're gonna start. Hold on, where's my board? We do have to start.
Professor,
Yes.
can I teach class one day?
Oh, you know what? So that is a very good question. I don't know if he's joking or not, but he's about to walk into it. He's not joking. He's about to regret that he just asked that. Also, wait, why is my basic answer is probably yeah. Oh, Felix, well, okay, let's everybody not take this the wrong way, but I'd rather it be Chris than Felix by a long shot. But Felix does teach. I mean, his presence like dominates us even when he's not. Okay, and he will walk in any minute. No, Chris, that's interesting. You should talk to me on the side because I would be very interested in that. And honestly, the only reason I even I wouldn't even pause on that. Like that would be a definite yes, especially if you were sort of serious and took it sort of seriously. I mean, as seriously as sort of I do. The only reason I'm pausing is because we're on Zoom. Like it's a little trickier to arrange on Zoom. If you were pre-COVID, I would say definitely yes. And I used to do that a lot. But we should talk on the side about that. I mean, that's a very hard thing for me to say no to. Anybody who'd want to do that, it's good for everybody for you to do that. But now he's like, it was a joke, dude. Shut up. Oh, I believe. And then, well, then, all right, I should move on in a minute. But first of all, I believe it. Second of all, then we should also talk about the MSRC. For real, they need you. Third of all, keep hanging. And this is true for everybody too. This is not just about Chris, but I hope you all understand too. This is how it goes. You hang around and do well in this class, then you hang around and do well in physics 204, then you keep hanging around and get through or do well in PChem and instrumental and all that. Then you become a CLT, then you hang around and you try to get it, and you get a recommendation for me to go to graduate school or to get a real job or whatever. And then that doesn't work out. So you keep hanging around and then you teach with me. Oh, is it really? Oh, and that is my birthday message to you, Chris. Yes, happy birthday, Scorpio that you are. And how appropriate that Chris would be born on All Saints Day. I don't even know what to say about that, but also the day before Day of the Dead. I don't know what to say about that. Anyway, happy birthday, Chris. And yes, let's think about that, honestly. Okay, and that applies, and that's not just about Chris. If anybody's interested in any of the trajectory that we just said, I'm not joking. He's the trick after Halloween. That's funny. All right. Speaking of the trick, though, why is my board completely dark? Sorry. Why is, oh, okay, that's why. That's really weird. Okay. Clearly I have not awakened yet today. All right, we're gonna start. Wait, and they're already I haven't even setting happy birthday, Christ. Okay, that's interesting. I think that's December 25th, but okay. Okay. All right. Yeah. Apparently, I don't want to do physics any more than you guys do, but I do. There is a home. Yeah. Happy birthday. That's very, what a nice group of supportive colleagues you have for a Scorpio. Okay. We do have to start, don't we? Okay. Well, yeah, apparently I don't feel like starting either. All right. Okay. If you can't hear me right now, by the way, or if you couldn't hear me a minute ago, it's because I'm not saying anything. I'm just writing things down to get us all warmed up. Okay. Okay, so it's all about Newton's second law now. First law tells you what happens when there aren't net external forces acting on an object. Third law tells you really what we mean by a force.
second law tells you what happens when net external forces do act on an object or act on a mass, okay? What do we mean by net external force? Well, external means from the outside. Force means interaction. Specifically, the third law tells us that force means symmetric interaction. It means a push or a pull that goes in both directions equally. An interaction means a push or a pull. External means from the outside. So force means an interaction that comes from the outside. Outside means another object. Okay, so the third law is really telling you in the end how to picture what forces are. A force is two objects pushing or pulling on each other. And the way to know whether two objects are pushing or pulling on each other is in all cases except one, physical contact. If two objects are touching each other, then they are pushing or pulling on each other, and we're in the present, and we're seeing a force. If you think that two objects are exerting a force on each other, then they must be pushing or pulling each other, with one exception, and that is gravity from the center of planet Earth. And that exception's always with us, so we always have to remember it. And in fact, it's so important, and it's such the one singular exception to all this that we always deal with it first in every problem we solve, because it's always there and we want to remember it. And then we get on to the regular pattern, which is that force means symmetric pull or push between two objects that are touching. Okay, so that was it. So the first law tells us what we would expect an object to do if it's not being touched, and what we expect an object to do is to not accelerate, to maintain constant velocity. The third law tells what I just said, how to know whether there is a force acting on an object. And the second law says that an object will accelerate exactly to the extent that net external forces are acting on it. So literally the second law, the one right here on the page, says that the acceleration of a mass is directly proportional to the sum of all of the external forces acting on it. Like that big sigma sign means net or means sum of. What we have to practice solving problems with is the second law, which predicts that if you add up all the forces acting on an object, taking into account the fact that some of those forces will be going in one direction that you would call positive, and the other forces would be going in the other direction, which we would call negative. If you add up all those forces and divide by the object's mass, you'll have the acceleration of the object along the axis on which all those forces are acting. So Newton's second law implies a procedure. I'm just going to look in the chat. Let me just look in the chat. Oh, right. And so what I'm calling, you could call it F total. Yes. Every time I'm saying net external force or sigma F, you could call it net F, you could call it net external F, you could call it F net, you could call it sum of the Fs, like SUM, or you can call it F total, sure. As long as we all recognize that when you add up all the Fs acting on an object, some of those Fs might have minus signs. They might be going in opposite directions. So it sometimes looks like subtraction, but it's always addition. It's just addition of numbers, some of which could be negative. Final point I'm going to make, and now we're going to start practicing, see how to practice problems with it. It's a vector equation. Force is a vector and acceleration is a vector. It has magnitude and direction. So really, whenever we say add up all the forces and divide by the mass, and that gives you the acceleration, That's all true on any and all axes simultaneously yet independently. To say F net equals MA is really to say three simultaneous but independent equations. F net equals MA on the x-axis, F net equals MA on the y-axis, and F net equals MA on the z-axis. So these are what the law says. The thing is, all the thought and the issues of this law go into really figuring out what all the forces are that are acting on an object. Is if you really know what all the forces are acting on an object along each axis, you just add them all up, divide by mass, and you get the acceleration. No problem. But the issue is, what are all the forces? There could be many forces on an object and many things you have to add up. So in other words, so what I'm saying is, okay. So the issue that we're going to get into now, the issue is, if you give it a certain problem, you have a certain mass, and you're trying to figure out its acceleration, how do you know what forces are acting on the M so that you could divide by M and get the A? Like, that's the issue. That's what we have to practice. It's like starting right now. Just give me a second. I'm just going to change the view of the screen. And the answer is diagrams. Hold on one second. Just give me a second. Oh. Okay. Tell me if you have to go back a page. It's fine. Okay, I'm gonna get straight to, okay, sorry, I'm looking at the chat. I'm doing two things at once as usual. I should never do. Oh, sorry. Yes, absolutely. Okay. In fact, yes, I need that too. All right. Let's pause for a second so people can get that back page. Let me know when you, and then I'm gonna explain. Wait. Wait. One second, sir. Sir. Hold on one second, sir. Okay. Are we back to the page? I'm doing two things at once. I'm just looking at the chat. If there's, whoa. I'm sure it was. Oh, you got it. Okay. All right, and I'm gonna pause for one more. I'm gonna. Okay. So here's the situation. I'm gonna get straight to. I'm gonna start right away with complicated examples. I think that's actually gonna be better for this. Anyway, so I'm gonna show you two types of diagrams. Okay. I mean, and again, I think you saw them in lab, but I don't know how comfortable you are with them. But since you did see them in lab, I'm going to sort of jump straight to lab applicable sort of complicated examples. The point of both, there's two different types of diagrams, and the point of them is to make sure that we've properly identified ultimately the magnitudes and the directions of all forces acting on a given M. Because again, the whole goal of Newton's second law is if you know all the F's acting on an M, then you can divide by M and you can add them all up, divide by M and predict the A of that M. And by the way, I should say at least once, the reason we ever want to predict the A of an M, the reason we ever want to predict the acceleration of a mass was twofold. One, we don't care about the velocities of masses ultimately. Velocities don't drive physics. The whole purpose of like the first half of this course is actually to show you that velocity is just is a matter of perspective and frame of reference. Velocity, objects by themselves don't have velocities as such. So velocity doesn't drive what's going on. It turns out that acceleration drives what's going on, and all the equations, if you look back now, all the equations that we've been building up for the beginning of the physics class are all constant acceleration equations. The whole idea is that if you know the acceleration of an object, then you can use something like x equals 1/2 at squared plus v naught t or whatever to predict how far away the object will be in a certain amount of time. And that's the point of physics, to know where something will be when. Or if you're solving crimes, like forensic physics, right, then it's to retrodict where something was when. But physics is all about what are the space-time coordinates of objects moving through space. So what we found in the beginning of the semester really is that what's going to do that for us is knowing object's acceleration. If you know an object's acceleration at an instant, then you'll know where it was when and where it will be when. That's like the whole issue of physics for real. So now we're saying, well, how do you ever know the acceleration? Like everything we were doing before was just like description and applying definitions. How acceleration's like the effect. What are the causes? Of acceleration? What we're now saying is the cause of acceleration is the sum of all the forces. So what we need now is mechanisms for identifying what the forces are acting on an object. So the first mechanism, the first diagram way of picturing it is this thing called the system schema. So we're going to do an example of a system schema on this given scenario. Here's this, and we're starting right away with a sort of complicated scenario to show the power of these techniques. So let's say, so to get all the issues out on the table. So let's imagine that there's a sled on the ground, on rough ground. That red word says rough. Like, in other words, I'm going to get, anyway, let's assume that there's a sled on rough ground, not perfectly smooth. A sled is on the rough ground. And attached to the sled is some piece of string or some rope up on some angle, and the rope is being pulled by a child, and so the sled is like sliding along the ground. Okay, and so first of all, here's so what I'm drawing now is just our typical DFP, I'm just drawing a picture just so you can picture what I'm talking about. This is not a system schema or a technical diagram or anything. Right. Oh, and look. Okay, so the key point that doesn't. And I should say also, and let's assume the sled accelerates horizontally along the ground. Right, so the situation is that there's this mass, this sled being pulled along the ground by a child, and the child is pulling at an angle. We can even say that that angle is called theta. Right, and the first key point is that the sled is the object of our attention. The sled is the thing, is the thing that we're focusing on. The sled is the mass whose acceleration we ultimately wish to compute. So we call the sled M, right? This, okay, everything else is some other kind of object. The sled is. Okay, so this is the situation. Our ultimate goal is to figure out the A of the M, and maybe I have to give you other numbers or something. But the question for a situation like this is, all right, if we're going to use F net equals MA to predict the A of this M, what are we going to plug in for net F? Or as Chris said, all F. What did he say? A total F, F total. What are we going to plug in for F total? What are the Fs? That's the question. So the first thing we do to figure out the Fs is first, we draw a system schema. A system schema for M. What does that mean? Okay, so what does that mean? Okay, so the first thing we're going to do, and the first thing we're going to do is we're going to identify every single object that's exerting a force of any kind on M. The way to do that is first, every single time we remember the center of planet Earth. The center of planet Earth is always, oh, here comes Felix. Okay. The center of planet Earth is always pulling on every object near Earth through this force that we call gravity. Gravity, we observe it all the time. We've been, aware of it since the beginning of the course. We've been aware of it since the beginning of history. We haven't broken down all the details of gravity yet. That's a never-ending historical process. Like everybody's always interested in breaking down the details of gravity. But one thing we know about gravity is it's always there. And it seems the gravity from planet Earth always seems to be there. And it seems to be a pull that doesn't involve touching. So it's always there. It's always important. It doesn't involve touching. So we always write it down first. But then after that, hang on one second. Hello, welcome back. I'll see you soon. Hello. Hello. Good to see you. How was it? Good. Okay, I'll see you soon. Okay, here it comes.
If he gives any of you homework, report to me immediately. No homework for the rest of this semester.
Okay, good job. All right, love you. Love you. Okay, good save, good save, good save. Okay, all right. Oh, and they say hi. They say hi. Oh, and they say it's their birthday, so no homework. Okay. All right. So oh, he says happy birthday. It's very nice. Okay. Oh, they say thank you. Okay, but close the door, please. Okay. Oh no, now the dog is gonna come. It's like a parade every time they say thanks. All right, awesome. I'm not telling him. Well, he will be upset when he has to sit around and watch me grade it for hours instead of playing Pokemon. But okay, and I'm gonna be upset because he just opened the door and the dog is gonna go. All right, anyway, all right. So what you do every single time is you. So you're going to identify Earth and get it out of the way in a sense, and then outside of Earth. The only objects we're going to write down that are exerting forces are each and every object that's actually touching M. And I mean that very literally. I mean this whole thing very literally. Like this is like an algorithm you can depend on. And it does address the hardest issue of Newton's laws. The hardest issue always is like, what are the forces? And the answer is shockingly simple. The answer to what are the forces? Oh my God. Oh yeah, don't play Pokemon Go. Sorry. Okay. The hardest issue always is what are the forces? And the answer is always so shockingly simple that it eludes us until we get used to it. The answer, but it's totally a reliable answer. The answer to what are all the forces is center of planet Earth and everything else touching the M and nothing else. So, okay, so I'm going to write those. I'm going to identify those in a second. But before I even write them down, I'm going to say for each object identified as exerting a force, depict by drawing a circle somewhere on the page. This is also literal. So here we go now, okay? Oh, okay. So what I'm going to do right now, again, what we're doing here is we're drawing a system schema. The system schema is going to be one step towards setting up the math to do F net equals MA. Again, remember, my whole point in this whole class, in a way, is people come into physics thinking that the hard part is going to be the math. Then from the minute they get into physics, classically, many of us, not all of us, but many of us, from the minute we get into physics, even thinking that we were afraid of the math, what ends up happening is we rely on the math and the algebra to crunch through the middles of problems, but we often don't feel comfortable knowing how to set up or begin problems. We get into this habit of thinking I can do the math, but I can do the equations, but I never know which equations to do or how to set them up or how to begin. And so the whole real issue of physics really is, how do you set up the math that then does the work for you in physics? Like really, the more you get, the more you see, and the more people say, like, I can do it, I just don't know how to start. What they really mean is I can crunch the math and the computations, but I don't know how to set up the math. So a lot of the time that I spend in this class talking to you, especially the stuff that doesn't look like you know how to write it down, or doesn't look like it's connected to any particular problem solving, most of what I'm talking to you about in class is ways to know how to set up the math. Well, here now, it's hopefully, if you're with me, it's going to be super concrete. The math that we have to do is F net equals MA. Like for the rest of this course, basically, the math we have to do is F net equals MA. The issue is, what do we plug in for F net? What do we plug in for the left side? How do we set it up? The answer is you take these diagrams super seriously. The first one is system schema, the one we're talking about right now. So what you do to make a, and really, unlike the beginning of the class, if you really follow what I'm saying, or once you follow what I'm saying, it's actually a much more strict, reliable procedure that actually takes the thought out of things for you, if that's what you want. Then the first half of the course, like honestly, if you follow this procedure I'm talking about, you actually, it does the thinking for you. So in the situation with the sled and the child and the him, what I'm going to do to make a system schema is this. I put a dotted circle in the middle of my page. The dotted circle is the M, is the sled. Okay, the dotted circle represents the sled. Then I'm going to draw a circle anywhere I want on the page for each and every one of those objects that's exerting a force. Okay, so first I always draw a circle that indicates the center of planet Earth, because it's always there. It's always exerting a force on anything and everything, on any mass, okay? And I draw it anywhere I want, because for this, the purpose of this picture of the system schema, the purpose is to identify the forces. I don't care yet what direction they're acting in. So I just draw this Earth anywhere I want. I could even draw it above the mass. And in fact, maybe I should, just to make the point clear. Sorry. So here's the center of Earth. Doesn't matter where I draw it. Then I'm going to draw a solid circle for every, after I've drawn Earth, always every single object that is touching the mass. And the mass is the sled. Okay, so, and I mean, and put this in your notes, please. I mean directly touching, literally touching directly. So what's directly touching this mass? I mean, it's a rhetorical question. One thing that's directly touching the mass is the string that is attached to it. Right? That's a different object. That's not part of the sled. That's a string we mentioned in the paragraph. So I draw a circle for a string. The string happens to be pulling on some sort of specific angle. I don't care about that at all for the system schema. But I just draw string. And I mean, I label it string. Okay? What else is touching the mass? Well, there's a ground below the sled. The ground is touching the sled is touching the ground, right? So I draw a circle that depicts the ground. Notice, and again, this is like weird, right? I mean, maybe it doesn't even look like science to you yet. I don't know, but it is, maybe I don't know if it's weird or not to you, but it is very specific. It's like, I'm following rules. I'm not just making this up. It's not a rough sketch. I'm literally identifying every object that is exerting some kind of force on the sled, and I'm only identifying objects that are exerting forces on the sled. So the ground is touching the sled in some kind of way. It's pushing it like up. So that's going to be a force. The string is touching the sled. It's pulling it like up and then over. So that's going to be a force. Planet Earth is always there. It's underneath the sled. It's pulling down gravitationally. I don't know all the details of gravity, but I know it's there. So planet Earth, center of planet Earth, is exerting a force. Now, that is it. There's a child in the problem. I know there's a child in the there's always a child in the problem. There's a problem in the child. But there's a child in the problem. And I mentioned that because otherwise we would have no reason to understand, well, how could a string just be magically pulling the sled? There's a child pulling the string, but the child is not touching the sled. The child is mentioned because otherwise the whole problem doesn't make any sense. But the child is not touching the sled. The child is touching a string, and the string is touching the sled. So the string goes in this diagram, the child does not. In fact, honestly, that's also part of the reason I mentioned the child in the problem, because right from the get-go, I want to get used to the idea that forces can feel very weird at first. Like you look at a random problem, it's like, I don't know, am I supposed to count the child? Am I supposed to count the string? I don't know, what is it for there? But the whole idea is only and everything, anything and everything directly touching our object is what we care about, plus center of Earth. That's it. That is our list for always, no matter how complicated things get. Also notice in the system schema, there's no fancy words yet, like friction or anything like that. It's just the objects that are interacting, like Newton's third law, interacting with the mass. So we're making progress. We now know, if I don't do anything else, what I already know now is there's going to be 3 forces that I'm going to have to deal with in F net equals M when I finally get to the math. Already, this is, well, I shouldn't even say that. I shouldn't even say that. There's 3 objects that are generating forces that I'm going to care about when I get to the math. That's like the knowledge that I'm already gaining from this picture. But now I'm going to go a little bit more specific. Okay, we've now drawn circles to depict each. I'm going to say one more thing. I'm sorry. The other purpose of this so far is forcing us. It's forcing us to realize that when you're identifying forces, first and foremost, you have to identify objects that are exerting those forces. A force is an interaction between 2 actual thingy things, right? So we never ever start, if ever you're doing math and you start invoking forces that are just coming from the sky, that are just coming from space, that you just believe have to be there because they're there, then something's wrong. A force only acts on an M if it's coming from some other kind of M. Okay, so now we've identified 3 objects that are interacting with the M. So we're going to start turning those interactions into mathematical forces that we can compute with. So how do we do that? So the next step, now that we've drawn circles, now we draw lines. And again, every time I say M, by M, I mean the object of our focus, the object whose acceleration we want to calculate. Like that's what I mean by M every time, right? So we're trying to figure out what's happening to M. We're asking what forces are acting on M so that we can figure out how M accelerates. Okay, so my next job in this system schema is to draw lines that depict actual forces or actual interactions. So I'm going to connect up these circles with lines. How do I do that? There's a rule. Okay. This is a little weird now, what I'm going to do. My goal here is to connect the circles with M by lines. The key, I need to do that because once I have a number of lines in my picture, it's the lines that will represent interactions. Each line will represent an interaction between two objects, a symmetric Newton's third law push-pull pair. Okay, and then it's each one of those lines that I'm going to sort of transfer into the next diagram, and from that build the math to do F net equals MA. Okay, it's a process. And again, I'm just going to say somewhat defensively because I'm like the used car salesman of physics. This may seem to some of you like a kind of an ornate, kind of long, complicated process. And maybe some of you eventually in your life want to skip certain steps in the process. That's fine. But the reason but the trade-off is this: I'm giving you a long, ornate process so that you don't have to think. Like the process does the thinking for you. If you can think and you can think successfully around it, but Quark bless America. I just think that I found in my own personal experience and in the experience of many others, the thinking gets challenging. It's not always what we always want to do. So here, at least until you know exactly what to think about, here's the process that does the thinking for you. So the process begins with the circles. Now we're going to have to connect the circles with lines so that the lines are going to become our forces. So how do we know how many lines to draw? We follow a very strict, simple rule, which is the one touch, one line rule. For every one touch that we're observing or picturing in our mind, there's going to be one line. I mean, it's that simple. The catch is that there's exactly two exceptions to this rule, which is kind of funny because often we don't even end up with many more than like one or two lines. So there's two exceptions, and the exceptions are very important, and the exceptions are almost always an issue, but they're very strict, exact exceptions. So I'm going to, so first let me give you an example of the rule, and then I'll give you the two exceptions, but they're always the same exceptions. So the one touch, one line rule is like, if I look at my picture, the string, okay, the string follows the one touch, one line rule. The string is touching the sled in a very simple way. Like here's the sled, there's the string, it's pulling on the sled. So that's a force. The force exerted by the string happens to have a name. We ultimately call it the tension in the string. I don't even care about that yet. I just know I look at a string touching a sled. The string is pulling on the sled. That means a force is acting on the sled. So I draw a line. Here, string is pulling mass. I draw a line indicating that pull. Let me say that again. String is touching mass. So I draw one line indicating that touch. End of story. So now I see at least one force in my picture, the force that the string is exerting on the mass. And look at the way the picture is. It's sort of a reminder of Newton's third law. Newton's third law indicates that if the string is pulling on the mass is pulling on the string in the same way. It's like a tug of war. Totally true. Like the system schema is capturing all of that for me. My ultimate focus is the mass, though. The dotted circle in the middle. So I want to continue to look at any other forces that are acting on the mass. So I've done the one touch, one line rule, but now it turns out that the other two objects involved are the two exceptions to the one touch rule. So what are those exceptions? The two exceptions, and again, there's not a million exceptions. There are exactly two exceptions that you always have to know about. Just like a force is a touch with one exception, gravity, but gravity is like always there. It's a huge exception. So we always make note of it right away. And then we get to everything else that's not an exception. Same thing here. There's two really important exceptions to this one touch, one line rule. So let's always be aware of them. Exception one, you might already guess it. Exception one is the center of Earth always is there. It's always there. And it always exerts a pulling force called gravity without touching, right? You already knew that. I mean, we've been saying it for hours. But let me make it clear now, that's an exception, right? Center of Earth, so whenever I see center of Earth in my picture, which I always will, even though there's no touching, even though there's no touching involved, I'm always going to draw a line from center of Earth to my mass, because I know the center of Earth is pulling on the mass, always, it's always pulling with this force called gravity. So there's always a line, always, between center of Earth and mass, even though I don't see any touching going on there. Again, it's an exception, but it's always there. So there's always, so it's not as complicated as it sounds. So we're almost there. We almost have our system schema done. We almost have all of the objects depicted. The other thing is like perhaps the most complicated. The other exception, and again, it's almost always there. It just doesn't follow the pattern. What's the pattern is one touch, one line. The other exception is that whenever two surfaces, i.e. 2D objects, two planes, push against each other, they exert two forces, i.e. two lines in the picture. Okay, this is a little complicated now. This is very complicated compared to the other things. So let me back up again. The string was not a surface. It was a line, like the string that was pulling on the sled, and it wasn't pushing, it was pulling. In fact, I'll let you. Okay, let me get something at. So I'm making a contrast here. When a string pulls on something, first of all, that's a pull. Pull means toward and push means away. So when a string pulls on a sled, it's literally a pull, and a string is a one-dimensional object, right? Like maybe not perfectly, but it's like it's a line, right? It's like an axis, a string. So that follows the one touch, one line rule. When a string pulls on something, it's only pulling in one way. It's pulling in whatever way the string is pulling. Okay. And so it only gets one line in the system schema, and that one line will represent a force that we will ultimately call tension. The force exerted by one end of a string is a force that points in a direction, the direction of the string, and gets one line in a system schema. It's one force, and the force is called tension. Okay, that's a contrast. In contrast, whereas when two surfaces push against each other, when two when two surfaces, like planes, surfaces, two-dimensional objects, push against each other, well, when two rough surfaces, I should really make that super explicit. When two rough surfaces push against each other, two things actually happen at the same time. In reality, if two surfaces are at all rough, like my hands, right? Or like the sled against the ground, or sandpaper against sandpaper, or whatever, or like a carpet against the floor. When two surfaces are pressing against each other, they press against each other, they press into each other against the plane of contact. But if they're at all rough, then if you sort of zoom in microscopically and like think about sandpaper or which is the extreme case, or even a carpet on the floor, if you zoom in and look microscopically, when they push the two surfaces together, the surfaces are bumpy. They're not perfectly smooth, so they interlock. So it's like pressing the two combs against each other. The teeth of the combs will interlock. So the more you push two surfaces against each other, the harder it is to rub or slide them along each other. So whenever you get this, you automatically get some of this. Now, that's not true with tension and pulling, but it is true with surfaces pushing. So whenever you push two surfaces together, you get a force perpendicular to the plane of contact, right? If the plane of contact is just that, the plane, the Euclidean plane, the surface against which they're both making contact, if you picture whatever they're doing, if you picture that plane, like plane, then each surface is pushing on an axis perpendicular to that plane. The press is called, that force is called the normal component of pushing, or the normal force. Okay, and normal does not mean regular, it does not mean typical. Normal just means perpendicular in math, right? But at the same time, the rub, the pushing resistance parallel to the plane of contact, that's called, as you know, I think you know, that rubbing phenomenon that always accompanies the normal pressing phenomenon is called friction. So all of this is to say, and I know there's 11 minutes left, all of this is to say, when surfaces push against each other, which they do all the time, of course, in the real world, when they push against each other, that's a slightly complicated, or it's a comparatively complicated phenomenon, because it actually will always bring two forces together. Like you can't push rough surfaces together without causing them to rub or resist and cause pushing along the other axis. For every bit that you get on this axis, you automatically get something on the other axis. This axis push is called normal. This one's called friction. And again, let me emphasize, normal does not mean like, I'm not saying there's always a normal force in every single physics problem. People think that all the time. I'm not saying normal means like gravity is in every single physics problem. There are lots of physics problems that don't have normal in them because there's lots of physics problems that don't have surfaces involved. Like if you go fishing and you just pull a fish out of the water with a fishing line, there's no normal force going on there, or holding a balloon. Like normal doesn't mean it's always there. Normal means perpendicular. What I am saying is that if two surfaces push against each other, then if they push it all perpendicularly to their plane, which we usually call in English like pressing or pressure, then automatically, if the surfaces are at all rough, automatically they're going to get sliding or rubbing forces as well because they're going to interlock to some microscopic extent. And so whenever you have a normal force, you automatically have a friction force. All of this means, therefore, this whole thing, this is the other big exception to the one touch, one line rule. It all means this all means, hence, in the diagram, in the system schema, hence, if you see two surfaces pushing against each other at all, which we do have in our situation, then two surfaces pushing always gets two lines in the system schema, i.e. two forces that we'll have to track in the math, okay? So I'm going to put them in, and then we're done, thank goodness, with at least this idea of the diagram. So you see the ground is pushing against the mass, similarly by Newton's third law, the mass is pushing against the ground, but the ground is pushing against the mass, but it's the ground is a surface, the mass, the sled is a surface. So I put two lines there. One represents the normal interaction between the two, and the other represents the frictional interaction between the two. That is my system schema. Okay, we're done. I know we have 9 minutes of class. That's my system schema. What? Done. Okay, and I know we've 7 minutes left here. Okay, that took a while. That's like in a way the most conceptual or hardest part or whatever. We've now gotten a lot of information on the table. Bottom line, this is supposed to be 4. We've now completed our system schema. I'm not going to keep flipping back, but the system schema, it forced us to draw these objects so that we know, it forced us to identify all the forces, but only the forces. We didn't make up any forces, which people do all the time. We didn't leave out any forces, which people do all the time. We restricted our attention to objects that are interacting with our mass. We identified those objects, and then we drew lines for each of the interactions. So at the end of the day, when we were finished with our picture, we look back at our picture, the purpose of it, the purpose that picture just achieved, was that it has a total of 4 lines in it. That is its purpose. That it generated 4 lines. Those 4 lines now tell us, okay, in our next step of analysis, or from here on in, we're going to be analyzing exactly 4 forces. We're going to take those 4 lines out of that picture and make sure that in our next picture and in our math, each one of those lines gets represented by a vector that indicates magnitude and direction, and is then computationally analyzed by virtue of its components, like we were practicing with other vectors. Okay, it all connects. So the system schema has done its work now. It gave us 4 lines. We now put it to the side and we say, okay, now, and I know we have 6 minutes left. Now we're going to draw a new picture. Built from that picture. Now we can draw, and it's our final picture. Now we can draw, with the 6 minutes left, we can construct our second and final diagram. Our second. And by a quick aside too, I know that a lot of you have done some of this in high school. And I know a lot of you in high school did the thing I'm about to do, which is free body diagrams. This will be, and I also know you did in the lab, but this will be familiar to some of you, the free body diagrams. But a lot of you who paid attention in high school or whatever might be thinking, okay, I know free body diagrams. What's all this system schema nonsense? We never did this crap in high school. I know. A lot of people don't do system schemas. It may seem like more work to you now, but I'm also going to tell you that my experience in high school and in college is a lot of people don't do the system schemas. They go straight to the free body diagrams, and the free body diagrams are wrong. Wrong. And if your free body diagram is wrong, everything topples from there. And maybe you know why, maybe you don't. I'm telling you the system schema ensures that your free body diagram, which is what we're now going to do, is actually correct. So if you've never seen the system schema before, that may well be. But join with me in embracing its power. So now from the system schema, now from it, we can construct our second and final diagram used for the math. It's called the free body diagram. Well, actually, it's not even final. It's really I shouldn't even say our final diagram. Our second diagram, and I'm even going to say, the pure free body diagram. Sorry. The pure free body diagram. How does this work? Now, I know I have to do this somewhat quickly, but this is a lot easier now that we've done system schema. How does this work? We start with a point in the center of our page, on the page, depicting or representing M. Okay, so I'm going to do this on the next. Okay, so first, I'll let you. So I'm going to draw a dot somewhere on my page, and the dot represents M. Tell me if you need me to go back. It's totally fine. Just let me know. Oh, wait. Oh, sorry. Oh, someone asked me 13 minutes ago. I'm so sorry. Wait a minute. So sorry. You know what? I totally apologize. I see someone's at 13 minutes ago. Someone asked me to go back. I was like on her. Okay. Thank you. Yes. Okay. I appreciate that. Yeah. Because I'm kind of, okay. I'll catch that next time, but thank you for being so understanding. Okay. So I'm going to draw a dot, which represents M, in the center of my page now. So now I've moved now I'm just drawing a dot. And there's a reason for that, because I really just want to focus all my attention on what's happening to sort of the center point of my sled. So I draw this dot representing the mass of the sled. And now, for each line in my system schema, we draw a vector now. So we're turning those lines into vectors. A vector whose tail is at M, whose tip points in the direction of the force, and whose length represents comparative approximate strength, magnitude. Comparative, because you won't know yet. We haven't calculated numbers. The whole purpose of this is to calculate numbers. So you won't know the exact magnitude of any of these forces, but you'll hopefully have an approximate idea of which one is stronger than how they compare to each other. So you try to capture, so you're going to draw arrows now, and we have 1 minute. So I'll just do it quickly. You're going to draw an arrow for that force of gravity from planet Earth. Planet Earth is under you, it pulls down. You're going to draw an arrow for that, and you're going to label each of these. So we'll label that arrow W for weight, weight of the object, the force of gravity. You're going to draw an arrow up for the normal force of the ground pushing on the sled, right? We said, right? But the ground is also pushing on the sled frictionally. So we'll draw an arrow going to the left and label it F for friction, right? And then we said there's a string pulling on an angle up and to the right, and that string force is called tension. So now, and I know it's 420. That's as far as I'm going with this, but just notice now we have a proper free body diagram. Each force is accounted for. Each force now is a vector with a certain direction that's intentional and a certain magnitude, which is approximate but intentional. And each arrow is labeled with the proper name for the force: friction, normal, weight, which is the force of gravity, and the tension in the string. So that's, so we got that from the system schema, and it's 420. So I'll leave it. There is homework that's due Monday. It hasn't been posted. I'm going to post it in a second. It's on all of this. I think between the lab and this, you'll be able to do it. You might have to look up a minor thing, or I'll write this up in the corner. This might help to know. I didn't explain it, but the weight of an object due to the gravitational pull is often written as, or is equal to, its mass times that 9.8 number. I got to explain that on Monday, but it might help you to know that for the homework. That weight of an object is the gravitational force, which is mass times gravitational acceleration. Okay, you've been very patient. I'm going to post the homework in a second, but thank you. Felix says thank you. I'm going to work on these exams. I cannot promise you're going to have them Monday. I apologize in advance, but I'm going to work as fast as I can and get them to whomever I can, blah, 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 blah. Have a great weekend. Happy Chris's birthday. And anybody who wants to teach, I will talk to you. Okay, thank you. Oh, and yeah, Melita.
Since it's my birthday, can we not have homework?
You cannot have homework tonight. You cannot do it tonight or even tomorrow, but then Friday night do the homework. But you can hand it in late, dude. You know that. You can always hand it in late. I don't know what.
Yeah, but it's homework.